Almost everything we're going to do in probability involves the relationships between different sets. So let's look at those. Let's let S be a universal set of all elements we could possibly be interested in. And let's let A and B be subsets of S. First of all, let's define A complement, also written as A bar, or pronounced not A, also written as S set minus A, be all elements of S except for the ones in A. So if this rectangle is S, and A is all the elements inside of this region, then A complement, or A bar, or S minus A, is everything outside of that region. Now if S is a finite set, actually let me define something before I say this. For any finite set, let's say capital U, we'll define U in between these vertical bars. We'll call that the cardinality of U. We'll define that to be the number of elements in U. So if S is finite, then A and A complement have to be finite also. Then number of elements in A plus number of elements in A complement equals number of elements in S. Which I guess we could also write as number of elements in A complement equals number of elements in S minus number of elements in A. And something similar is true for infinite sets. Obviously we can't count the elements because there's infinitely many elements in S and maybe infinitely many in A, infinitely many in A complement. But the areas of the region, if these are regions in the plane, satisfy similar properties. So if S is a region in the plane, then the area of A plus the area of A complement equals the area of S. i.e., so we could also say the area of A complement equals the area of S minus the area of A. And an easy fact about complements is if you take the complement of the complement, you get a set back. So if you look at all the elements except the ones that are not in A, that's just A. Maybe this looks easier to write if we use the bar notation. So not A equals A. All right, now let's look at two elements inside of S, A and B. So as you probably know, we define A union B to be all the elements X in our universal set S, such that X is in A or X is in B. And we define the intersection of A and B to be all the elements S, all the elements X, such that X is in A and X is in B. So if this is S and this circle's A and that circle's B, let me do this again so I can fit two of these side by side. Right, the circle on the left is A, the circle on the right is B. So A union B is all the elements that are in at least one of the two sets, and A intersect B is all the elements that are in both sets at the same time. Now if we take the complement of a union or an intersection, there's easy formulas to tell us what that is equal to. So the complement of A union B is complement of A intersect complement of B. So you just keep the complement sign over the sets individually, and the complement makes the union sign turn into an intersection sign. And the reason is that X is in the complement of A union B if and only if X is not in A union B. That's just what complement means. And that's equivalent to saying X is not in A and X is not in B. So in other words, X is in A complement and X is in B complement. But X being in A complement and X being in B complement means that X is in A complement intersect B complement. And then we have a very similar formula for the complement of A intersect B. So I'll put that right here. The complement of A intersect B is complement of A union complement of B. So again, when we take the complement of this expression, we take the complement of the sets individually, and then the intersection sign turns into a union, just like the complement made union turn into intersection. So X is in the complement of A intersect B. Let's say here's A intersect B. So X is in the complement of that if Okay, X is not in A intersect B. How could that be how could that happen? Well, X would either have to fail to be in A or it would have to fail to be in B. It could be in one of them, but it has to fail to be in the other. So if X is not in A, that's the same thing as X being in A complement. And X not being in B is the same as X being in B complement. And then X being in one set or X being in another set means that X is in the union of those two things. Now these formulas extend more generally to intersections of several sets or unions of several sets. So more generally, let's say we have a union of K sets. We want to take the complement of that. So the complement of the first one, change union to intersection, and take the complements of all the sets individually. Similarly, if we have an intersection of K sets, we want to take the complement of that, we take the complements of the sets individually and then put unions between all of them. And the reasons for these identities are very similar to the reasons for the identities involving two sets at a time. All right, now let's look at the set minus operation. So this is a slanted minus sign. So that's all the elements X that are in A, but X is not in B. This turns out to be the same thing as A intersect B complement. So to draw this, here's A, here's B. This shaded region is A set minus B, or if you like, A intersect B complement. All the elements in A that are outside of B. It's easy to see that A equals all the elements in A that are not in B union all the elements in A that are also in B. So considering how B intersects A, that breaks A into two regions. We've got the A intersect B complement, and then of course the A intersect B part of A. Similarly, that means that B is going to be A intersect B union B intersect A complement. So the elements in B consist of the ones that are also in A and the ones that are not also in A. This also means that we could decompose A union B if we wanted to as the elements in A that are not in B union the elements that are in both A and B, union the elements that are in B but not in A. Now if all these sets are finite, that gives us some counting formulas. So if S is finite, then anything inside of it is also finite. Then the number of elements in A union B equals number of elements in A intersect B complement plus the number of elements in A intersect B plus the number of elements in B intersect A complement. Also, we could say that the number of elements in A union B equals number of elements in A plus number of elements in B. Well, if we add all the things in A and all the things in B, we overcounted that region because we counted it twice. So minus all the elements in A intersect B. And the same is true of areas if these are regions in the plane. So if S and A and B are regions in the plane, then the area of A union B equals the area of A intersect B complement plus the area of A intersect B plus the area of B intersect A complement. The whole area of A union B is this area plus that area plus that area. We could also say it's the area of A plus the area of B minus that region that we counted twice. Alright, now just for fun, let's do this with 3 sets instead of just A and B. So let's look for a formula kind of like this for A union B union C. Now I claim that the number of elements in A union B union C equals number of elements in A plus number of elements in B plus number of elements in C minus the number of elements in A and B in the intersection minus number of elements in the intersection of A and C minus number of elements in the intersection of B and C plus the number of elements in the intersection of A, B, and C. That part in the middle there. And the reason is, let's put a tick mark in the regions counted by the positive parts here. So A, B, C, and A intersect B intersect C. So if we do that, so we count everything in A, this region, that region, that region, then count everything in B, this region, that region, that region, that region. So we've counted things here twice. Every element here gets counted twice, every element there gets counted twice. And then if we count elements in C, Now we've counted elements here twice and twice. We've counted elements there 3 times. And then when we count the elements in A intersect B intersect C, I guess we're going to count those elements again. So we've counted these elements 4 times, these elements twice, these elements twice, these elements twice, and elements here, here, and here only once. Now let's erase tick marks. In regions counted by A intersect B, cardinality, A intersect C, the cardinality, and B intersect C. Alright, if we erase elements in A intersect B because we overcounted them, we're going to erase 1 tick mark here and 1 tick mark there. Then if we erase elements that are in A intersect C, we'll erase 1 tick mark here and 1 tick mark there. And then if we erase elements counted by B intersect C, then we're erasing 1 tick mark here and 1 tick mark there. And what we're left with is every element counted exactly once, which is what we want if we're counting all the elements in A union B union C. And this works for areas of regions too. So if we just change all these cardinality signs to area, the area of A union B union C is the area of A plus the area of B plus the area of C minus the area of this intersection minus the area of that intersection minus the area of that intersection plus the area of the triple intersection, the little region inside. And this formula is called the inclusion-exclusion formula because we include some elements, we include too many here, then we exclude to compensate for what we included too many times, and then we include again to compensate for what we subtracted too many times. And there's a version for K sets for any K. So the more general inclusion-exclusion formula says that if we want a formula for the number of elements in the union of K different sets, then we can add up the number of elements in each set individually, but that's overcounting. So then we have to compensate by subtracting areas in the intersections of 2 sets at a time. But then that's actually subtracting too much, and then we have to add back in all the areas for intersections of 3 sets at a time. Etc. And we keep increasing the number of sets being intersected until we get to the intersection of all these sets. Plus or minus, because it depends whether K is an even number or odd number. We're always going to start with positive, negative, and alternate until we get to the final intersection of all the sets. And I guess if K is even, that's going to be a minus sign, and if it's odd, that's going to be a plus sign. And of course, this is true for areas of regions as well. Now another fact, which is sort of obvious but is going to be important for us, is that if we have one set contained inside of another set, then the number of elements in the inside set is less than or equal to the number of elements in the set it's contained in. Well, this for A and B are finite. And we could say the area of A is less than or equal to the area of B if A and B are regions in the plane. Another fact that's easy to state and is going to be useful to us is a distributive law that holds for intersection and union. Now recall that we have a distributive law for addition and multiplication. If we have A times B plus C, that equals AB plus AC. And also recall that if we swap the roles of addition and multiplication here, then we do not have a distributive law. We can't say A plus BC equals A plus B times A plus C. Of course, you wouldn't do that. With union and intersection, we have distributive laws also, and maybe the surprising thing is that both of them work. So if we have A union B intersect C, we could expand this out as A union B intersect A union C. And if we have A intersect B union C, we could expand this out as A intersect B union A intersect C. So both of the distributive laws will work with union and intersection, even though with addition and multiplication one of them works and the other one does not work. And that's enough about sets for now. The end.